Hello there. Welcome to the Sleepy Mind channel. I'm so glad you're here. Maybe it's been a long day, or maybe you just like to fall asleep thinking about stars, galaxies, and the quiet mysteries of the universe. Either way, tonight's journey is for you. There's nothing you need to do now. Just let your body rest, your mind slow down, and your thoughts drift. The quiet beginning of everything. The universe did not begin with an explosion in space, but with the expansion of space itself. There was no center point throwing matter outward into an empty void. Instead, everything that exists now was once contained within an incredibly hot, dense state, where distances meant almost nothing and time behaved very differently from how we experience it today. As the universe expanded, space stretched, cooled, and slowly allowed structure to form. This process continues even now, quietly and steadily, without urgency or sound. When scientists speak of the Big Bang, they are describing a transition, not a moment you could point to on a clock. The earliest phases of the universe are hidden behind conditions so extreme that our current physics can only describe them in fragments. What we can say with confidence is that the universe expanded rapidly at first, then more gently, allowing energy to settle into matter, and matter to gather into the first simple particles. For a long time after this beginning, there were no stars, no galaxies, and no planets. The universe was filled with a glowing plasma, a sea of charged particles moving freely, scattering light at every turn. Photons could not travel far without colliding into something else, and space itself was opaque, more like a thick fog than the clear darkness we imagine today. In this early era, the universe glowed evenly in every direction, warm and dense, with no distinct features. As expansion continued, temperatures dropped. Protons and electrons slowed enough to combine into neutral atoms, mostly hydrogen and helium. This change, known as recombination, transformed the universe in a profound way. Suddenly, light was free to travel long distances without being constantly scattered. Space became transparent for the first time. The universe, in a sense, opened its eyes. The light released at that moment has been traveling ever since. Over billions of years, as space stretched, the wavelengths of those photons stretched too, shifting from visible light into microwaves. Today, this ancient glow surrounds us in every direction, faint and nearly uniform, known as the cosmic microwave background. It is not light from stars or galaxies, but from the universe itself when it was very young. This background radiation is so evenly distributed that it suggests the early universe was remarkably smooth, with only tiny variations in density. These small differences matter deeply. Over time, gravity amplified them, pulling matter together slightly more in some regions than others. These subtle imbalances became the seeds of everything that followed. Without them, the universe might have remained a diffuse, featureless fog forever. In the quiet darkness after recombination, the universe entered what scientists sometimes call the cosmic dark ages. There were no stars yet, no sources of visible light, only vast clouds of hydrogen and helium slowly responding to gravity. This period lasted hundreds of millions of years, a long, patient wait before the first lights turned on. Eventually, in regions where matter gathered more densely, gravity compressed gas until temperatures rose enough to ignite nuclear fusion. The first stars were born. These early stars were unlike the ones we see today. They were massive, bright, and short-lived, burning through their fuel quickly. In their cores, simple elements fused into heavier ones, creating carbon, oxygen, and other materials essential to future complexity. When these first stars died, many of them exploded, scattering enriched material into space. This cosmic recycling seeded future generations of stars and planets. Every atom heavier than hydrogen in your body was forged in stars like these. The calcium in your bones, the iron in your blood, the carbon that forms your cells all began in stellar furnaces billions of years ago. As more stars formed, they gathered into galaxies, bound together by gravity and shaped by dark matter, an invisible substance that outweighs normal matter by a wide margin. Dark matter does not emit or absorb light, but its gravitational influence acts like a quiet scaffolding, guiding the formation of cosmic structures. Without it, galaxies might never have taken shape at all. The expansion of the universe, however, did not slow forever. Observations suggest that it is now accelerating, driven by something we call dark energy. This mysterious force appears to push space apart on large scales, overcoming gravity over vast distances. Its nature remains unknown. It does not clump or form structures. It simply exists everywhere, evenly, gently encouraging the universe to stretch faster over time. This accelerating expansion raises deep questions about the age of the universe. Based on current measurements, scientists estimate it to be about 13.8 billion years old. This number comes from combining observations of the cosmic microwave background with measurements of how fast galaxies are moving away from each other. Yet different methods sometimes produce slightly different answers. Some observations of ancient stars suggest they may be nearly as old as the universe itself, pressing against the limits of current models. Measurements of the expansion rate using nearby galaxies do not perfectly match those derived from the early universe. These discrepancies are small, but persistent. They hint that our understanding may be incomplete, that there may be subtle factors we have yet to account for. It is possible that dark energy behaves differently over time, or that gravity itself works slightly differently on cosmic scales. There may be new physics waiting to be discovered, hiding in these gentle mismatches. Or the discrepancies may fade as measurements improve. For now, the question remains open, resting quietly at the edge of knowledge. Time itself behaves differently in the universe than we often imagine. According to relativity, time is not a single universal flow ticking the same way everywhere. It is shaped by gravity and motion. Clocks run slightly slower in stronger gravitational fields and slightly faster in weaker ones. This effect is small in everyday life but becomes significant near massive objects like neutron stars or black holes. Even here on Earth, clocks at higher altitudes tick faster than those at sea level by tiny amounts. GPS satellites must account for this difference to function correctly. Time, it turns out, is flexible, gently stretching and compressing depending on where you are and how you move. In the early universe, time flowed differently still. Conditions were so extreme that familiar concepts like seconds and minutes lose their meaning. The universe evolved rapidly, changing in ways that are difficult to imagine from our calm, settled present. Yet even then, the fundamental processes followed natural laws, unfolding step by step without intention or hurry. As the universe aged, it cooled and grew quieter. Star formation peaked billions of years ago and has been slowly declining ever since. Galaxies now produce fewer new stars than they once did. Over trillions of years, this trend will continue. The universe is not rushing toward an ending, but gently drifting into a quieter phase. And yet, even in this vast timeline, moments of light and structure continue to appear. New stars still form. New planets still coalesce. New patterns emerge within old frameworks. The universe is not static, but softly evolving, always changing, always expanding. When you look at the night sky, you are seeing the past. Light takes time to travel. The moon appears as it was a little over a second ago. The sun appears as it was 8 minutes ago. Distant stars appear as they were hundreds or thousands of years ago. Galaxies millions or billions of light years away show us scenes from deep cosmic history. Some of the light reaching your eyes tonight began its journey long before Earth existed. It crossed expanding space, passed through clouds of gas, curved around massive objects, and continued onward, uninterrupted, until it met your retina. In that sense, the universe is always arriving, moment by moment, carrying ancient stories into the present. There is something quietly comforting about this. The universe is vast beyond comprehension, yet it unfolds according to consistent rules. It remembers its past in subtle ways, encoded in light and structure. It does not rush and it does not forget. It simply continues, patient and expansive. As we move forward in this exploration, we will gently leave the earliest moments behind and drift outward into the wider cosmos, into lonely planets, slow-moving galaxies, and mysteries that remain unsolved not because they are hidden, but because the universe takes its time revealing them. For now, you can rest with the thought that everything you are, every breath you take, is part of this long, quiet story. A story that began without noise, without urgency, and continues still, unfolding calmly, one moment at a time. As we move outward from the universe's quiet beginning, we begin to encounter its most humbling quality: scale. Space is not just large in a way that can be measured, but vast in a way that stretches intuition. Distances grow so immense that the mind gently lets go of counting and shifts into feeling. The universe invites patience, because nothing meaningful happens quickly across such spans. The speed of light, which seems instant in daily life, becomes slow when measured against cosmic distances. Light travels at nearly 300,000 kilometers per second, fast enough to circle Earth more than 7 times in 1 second. Yet even at that speed, crossing the universe takes time measured in billions of years. Distance in space is not simply space between things. It is history. Astronomers often use the term light year to describe these distances. A light year is not a unit of time, but of length, the distance light travels in 1 year. Even the nearest star beyond our sun is over 4 light years away. That means the light you see from it tonight began its journey before the most recent global events on Earth, traveling uninterrupted through expanding space until it gently reached your eyes. Our galaxy, the Milky Way, is about 100,000 light years across. It contains hundreds of billions of stars, many with their own planetary systems. If you were to travel at the speed of light, it would still take 100,000 years to cross from one side of the galaxy to the other. At the speeds we can currently achieve, such a journey would take longer than the age of human civilization multiplied many times over. And yet, the Milky Way is only one galaxy among hundreds of billions. Galaxies gather into clusters, clusters form superclusters, and superclusters trace vast filaments across space, separated by enormous voids. On the largest scales, the universe resembles a delicate cosmic web, threads of matter stretching across darkness, shaped by gravity and time. Between these structures lie regions of near emptiness, where very little matter exists. These cosmic voids can span tens or hundreds of millions of light years. They are not truly empty, but so sparsely populated that a single atom might drift for meters, kilometers, or even more before encountering another. Even emptiness in the universe has depth. Despite this complexity, the universe appears remarkably uniform when viewed from the largest scales. No matter which direction we look, the overall distribution of galaxies appears similar. This suggests that there is no special center, no preferred direction. Everywhere is, in a sense, the middle. Expansion happens everywhere at once. When astronomers say the universe is expanding, they do not mean that galaxies are flying outward through space like debris from an explosion. Instead, space itself is stretching. The distances between galaxies increase over time, carried apart by the expansion of the fabric that holds them. Galaxies remain mostly intact because gravity binds them together locally, even as the larger framework grows. A helpful way to imagine this is to think of dots drawn on the surface of a balloon. As the balloon inflates, the dots move away from each other, not because they are moving across the surface, but because the surface itself is expanding. From the perspective of any dot, all others appear to recede. No dot is the center. The same is true for galaxies in the universe. This expansion does not require energy to push galaxies outward in the conventional sense. It arises naturally from the equations that describe space and time. And over the last several billion years, that expansion has begun to accelerate subtly and steadily, driven by dark energy. As space expands, it carries light along with it. Photons traveling across the universe experience this stretching as an increase in wavelength, a process known as redshift. The farther a galaxy is from us, the more its light has been stretched by expansion. By measuring this redshift, astronomers can estimate how far away a galaxy is and how fast it is receding. When we observe very distant galaxies, we see them not as they are now, but as they were when the universe was much younger. Some of the most distant galaxies we can detect appear as they existed only a few 100 million years after the Big Bang. Their light has been traveling toward us for over 13 billion years, slowly crossing an expanding universe. In this way, looking deeper into space is also looking back in time. The universe offers its own archive, written in light. Every photon carries a memory of where and when it began. When we collect that light, we are gently reading pages from a book that has been writing itself since the beginning of time. The idea of an edge to the universe is a natural one. It is tempting to imagine a boundary, a place where space ends and something else begins. But observations suggest that the universe does not have an edge in any conventional sense. Space does not appear to stop. Instead, it continues, perhaps infinitely, or curves back on itself in a way that has no boundary. If the universe is curved, it may be finite but unbounded, much like the surface of a sphere. On Earth, you can travel endlessly without ever reaching an edge, eventually returning to your starting point. Space may behave similarly, though in more dimensions and on far larger scales. Traveling far enough in a straight line could, in theory, bring you back to where you began without ever encountering a border. This curvature, if it exists, is extremely subtle. Measurements suggest that space is very close to flat, meaning that over observable distances, it behaves much like familiar geometry. But even slight curvature, spread across the entire universe, could have profound implications. The observable universe itself is limited, not by an edge, but by time. Light has had only a finite amount of time to reach us since the universe became transparent. Beyond a certain distance, light has not yet arrived. This creates a horizon, not a physical boundary, but a limit to what we can currently observe. Beyond that horizon, the universe likely continues much as it does here. Galaxies, stars, and planets may exist far beyond our view, following the same laws, unfolding the same quiet patterns. There is no indication that reality changes abruptly just beyond our reach. The universe does not appear to hide anything at the edge of vision. It simply takes its time revealing itself. Distances also change with time in a subtle way. Because the universe is expanding, objects that were once close enough to exchange light may now be moving away from each other faster than light can travel through the expanding space between them. This does not violate relativity, because it is space itself that expands, not objects moving through space. As a result, some regions of the universe are already forever out of reach. Light emitted there now will never reach us, no matter how long we wait. Those galaxies will fade from view, not because they disappear, but because space carries them beyond our cosmic horizon. Over unimaginably long timescales, the night sky will grow darker as more distant galaxies slip beyond visibility. And yet, this is not a loss in the present moment. The universe offers more than enough to contemplate, even within our limited view. The sheer scale invites a soft humility. Human concerns, while meaningful and real, rest within a much larger context, one that does not judge or rush. When you consider the vastness of space, it becomes easier to release urgency. Distances that take millions of years to cross do not respond to impatience. They simply exist, calmly and expansively. The universe does not hurry, and it does not ask you to hurry either. Every atom in your body is separated from others by vast empty space at the smallest scales. Even within matter, emptiness dominates. The solidity you feel is an interaction of forces, not a continuous substance. In this way, space exists both between galaxies and within you, quietly present, holding structure without effort. As we continue, we will drift into regions where space feels more intimate again, where worlds wander alone, stars burn quietly, and mysteries unfold not with drama, but with patience. The universe does not reveal itself all at once. It invites slow attention, one gentle fact at a time. For now, let your thoughts stretch outward, then soften. There is no need to grasp the entire scale. Simply resting within the idea is enough. Space is wide, time is deep, and you are safely here, floating within it, supported by patterns older than memory. Gentle cosmic mysteries. Not everything in the universe announces itself with light. Much of what shapes the cosmos does its work quietly, unseen, leaving only subtle traces behind. These hidden influences are not gaps in knowledge to fear, but invitations to curiosity. The universe is not withholding secrets out of malice. It is simply vast enough that understanding arrives slowly. One of the most influential unseen components of the universe is dark matter. Despite its name, dark matter is not dark in the sense of being black or shadowy. It is called dark because it does not emit, absorb, or reflect light in any detectable way. We cannot see it directly, and yet its presence is felt everywhere. Astronomers first suspected dark matter when they noticed that galaxies rotate in unexpected ways. Stars at the outer edges of galaxies move much faster than they should if only visible matter were present. According to gravity alone, these stars should drift away into space. But they remain bound, circling their galaxies calmly and predictably. Something unseen is holding them together. This invisible mass extends far beyond the visible edges of galaxies, forming large halos that envelop them. These halos overlap and connect, shaping the cosmic web on the largest scales. Dark matter acts like a quiet framework, guiding the formation of galaxies without ever drawing attention to itself. We do not yet know what dark matter is made of. It could be composed of particles that rarely interact with ordinary matter. They pass through planets, stars, and even your body without notice. trillions of them may be moving through you right now, leaving no trace. This idea can feel strange at first, but it is not threatening. These particles are gentle in their indifference. They do not collide, burn, or disrupt. They simply pass through as neutral as the space they inhabit. The universe is filled with such silent travelers. Another mystery, even more subtle, is dark energy. Unlike dark matter, which pulls things together through gravity, dark energy appears to push space apart. It is not concentrated in any particular place. Instead, it seems to be woven evenly into space itself. Dark energy becomes noticeable only over immense distances. On the scale of galaxies or solar systems, gravity dominates. But across billions of light years, dark energy quietly takes over, accelerating the expansion of the universe. It does not push objects outward through space. It stretches the space between them. We do not know what dark energy is. It could be a property of space itself, a constant background energy that becomes important as space expands. It could be something that changes slowly over time, or it could signal that our understanding of gravity is incomplete. Despite its mysterious nature, dark energy does not disrupt local stability. Stars continue to orbit galaxies. Planets remain bound to their suns. Your body remains comfortably held together by forces far stronger than cosmic expansion. Dark energy works only on the largest scales, so slowly that its effects unfold over billions of years. Mystery in the universe does not mean chaos. In fact, the universe is remarkably stable. It follows consistent patterns. The unknown does not tear at the edges of reality. It rests within it, patiently awaiting deeper understanding. Another cosmic mystery lies in the nature of time itself. While we experience time as a steady flow from past to future, physics suggests that time may be more flexible. In certain equations, time behaves more like a dimension similar to space. Events exist within space-time, connected by relationships rather than sequence alone. Some interpretations of physics suggest that the past, present, and future all coexist in a broader structure, sometimes called a block universe. In this view, time does not move. Instead, we move through it, experiencing moments in sequence. The universe, in its entirety, simply is. This idea can feel abstract, but it carries a quiet reassurance. If moments persist, then nothing is truly lost. Past experiences remain part of the universe's structure, just as real as the present. The universe does not forget its own history. Quantum mechanics adds another layer of gentle mystery. At the smallest scales, particles behave in ways that defy everyday intuition. They can exist in multiple states at once, described by probabilities rather than certainties. Only when measured do these possibilities settle into outcomes. This does not mean the universe is random in a careless way. The probabilities themselves are well defined. Over large numbers of events, patterns emerge with remarkable consistency. Randomness at small scales gives rise to order at large ones. Particles can also become entangled, meaning their properties remain connected even across great distances. A change in one is reflected in the other, instantly, in a way that does not transmit information faster than light but still defies simple explanation. This connection does not fade with distance. It is as if the universe remembers relationships more deeply than location. These quantum effects do not disturb everyday life. They average out at larger scales, leaving the world stable and predictable. And yet, they form the foundation of everything we see. Beneath the solid appearance of matter lies a gentle uncertainty, a soft blur of possibilities resolving into form. Even the vacuum of space is not truly empty. According to quantum theory, it seethes with temporary fluctuations. Pairs of particles appear and disappear almost instantly, borrowing energy from the vacuum and returning it just as quickly. These fluctuations are usually imperceptible, but their effects can be measured in precise experiments. In this way, emptiness is active. Space is not a void, but a subtle field of potential. Nothingness, it turns out, is never entirely nothing. Another mystery concerns the fate of information. When matter falls into a black hole, what happens to the information it carries? For a long time, this question puzzled physicists deeply. Some theories suggested information might be lost forever, which would challenge fundamental principles of physics. Recent ideas suggest that information may not be destroyed but transformed, spread thinly across the event horizon or encoded in subtle correlations. Even here, where gravity is extreme, the universe appears to preserve its record. Mystery in the universe is not an absence of meaning. It is a sign of depth. Each unanswered question points to layers of structure we have not yet explored. The universe is not opaque. It is translucent, revealing some patterns while softly obscuring others. These mysteries do not demand immediate resolution. They coexist with understanding, enriching it. Just as a night sky remains beautiful even when we do not name every star, the universe remains coherent even when we do not know every mechanism. Curiosity does not require tension. It can be gentle, open-ended, and patient. The universe does not rush explanations. It unfolds them gradually across generations of thinkers and observers. As you rest with these ideas, there is no need to hold onto them tightly. Let them drift. Mystery does not ask to be solved before sleep. It asks only to be noticed. In the next part of our journey, we will move from invisible forces to solitary worlds, drifting quietly through space, shaped by gravity but unlit by stars. Worlds that exist not as exceptions, but as natural expressions of cosmic processes. For now, let your thoughts soften. The unknown is not pressing in. It is simply there, calm and expansive, waiting. As we move from the hidden forces that shape the universe, we arrive at places that exist in almost complete silence. Worlds without suns. Planets that do not belong to any star. They drift through space alone, carried by gravity but not anchored by light. These are known as rogue planets, and they may be far more common than once imagined. Most planets form within swirling disks of gas and dust around young stars. Over time, particles collide, merge, and grow, eventually becoming worlds with stable orbits. But not all of these systems remain orderly. Gravitational interactions between planets can be chaotic, especially in their early stages. Massive planets can disturb smaller ones, flinging them outward until they escape the pull of their star entirely. When this happens, a planet becomes a wanderer. No longer warmed by a nearby sun, it travels through interstellar space on a long, unlit journey. Some rogue planets may also form on their own, collapsing directly from clouds of gas like very small stars that never ignited fusion. However they arise, they share a common fate. They move quietly through darkness, unannounced and unseen. Astronomers estimate that there may be billions of rogue planets in our galaxy alone, possibly even more than the number of stars. They do not shine. They do not glow brightly. They reveal themselves only when they pass in front of distant stars, briefly bending light through gravity in a phenomenon known as microlensing. For a short moment, a distant star appears to brighten, then fades again, leaving behind the invisible signature of a passing world. These planets are cold on their surfaces, often reaching temperatures far below those found anywhere on Earth. Without sunlight, their skies are perpetually dark. There are no sunrises or sunsets. Time is marked only by internal processes and slow motion through space. Yet even in this darkness, these worlds are not entirely lifeless in structure. Some may retain internal heat from their formation or from radioactive elements in their cores. Deep beneath frozen surfaces, there could be warm layers, oceans sealed under thick ice, slowly circulating in complete isolation. If life could arise in such environments, it would exist without light, without seasons, and without any awareness of stars. This idea challenges the way we think about habitability. Life, if it exists elsewhere, may not always depend on sunlight. It may draw energy from chemistry, pressure, and heat. The universe may host forms of existence that unfold quietly, never seen, never signaling their presence across space. Beyond rogue planets, there are also worlds that orbit stars in unusual ways. Some planets circle their suns so closely that their years last only a few days. Others follow long, stretched orbits, swinging from intense heat to deep cold. Some rotate slowly, with days lasting months or years. Others spin so fast that their equators bulge outward. There are planets larger than Jupiter and smaller than Earth, planets with thick atmospheres of hydrogen, planets with skies of methane, planets where it rains molten glass sideways due to extreme winds. These worlds are not rare exceptions. They are natural outcomes of planetary formation under different conditions. Among the strangest are planets made largely of carbon rather than silicate rock. In these environments, carbon can crystallize under immense pressure, forming diamond-like structures deep within the planet. Such a world would not sparkle as a gemstone. Its surface would be dark, hot, and dense. But beneath that surface, vast crystalline lattices could extend for thousands of kilometers. These diamond worlds remind us that beauty in the universe does not always resemble beauty on Earth. What appears dull or hostile at the surface may hide remarkable complexity within. Some planets orbit dead stars. Pulsars, the dense remnants of massive stars, emit beams of radiation as they spin. Around at least one pulsar, astronomers have detected planets that survived the violent death of their parent star or formed from its debris. These worlds exist in extreme environments, bathed in radiation, orbiting an object smaller than a city but more massive than the sun. Even here, order persists. Orbits remain stable. Motion continues predictably. The universe does not abandon structure, even after destruction. Moons, too, can be lonely worlds. Some moons in our own solar system may harbor subsurface oceans beneath thick ice. Europa, Enceladus, and others show signs of liquid water hidden far below frozen crusts. These oceans are warmed by tidal forces, gentle flexing caused by gravitational interactions with their parent planets. Such environments are shielded from space, stable over long timescales, and chemically rich. They offer quiet refuges where complexity could slowly arise. These worlds do not rely on sunlight. They exist in darkness, warmed from within, patient and enduring. Loneliness in space does not mean absence. It means separation, not emptiness. Even the most isolated world is connected to the rest of the universe through gravity, motion, and shared origin. Every planet, bound or unbound, carries a history written in its atoms. As rogue planets drift through the galaxy, they pass through regions of gas, dust, and dark matter. Over millions of years, their paths curve gently, shaped by gravitational fields. Their journeys are slow and steady, without destination. They do not seek new stars. They simply move. There is something quietly peaceful in this image. A world traveling alone, complete in itself, not striving, not orbiting, not pulled into constant motion around another object. Just drifting, spinning slowly, carrying its internal rhythms through the dark. In time, some rogue planets may pass close enough to stars to be captured again, entering new orbits. Others may wander forever. Some may collide with other objects. Most will simply continue, unchanged, long after the stars they once knew have faded. The universe allows for such long solitude. It does not demand connection or activity. It supports stillness on grand scales. As we move on, we will turn our attention from planets to the stars themselves, not as dramatic explosions or brilliant points of light, but as long-lived processes, burning quietly for millions or billions of years, shaping the rhythm of galaxies. For now, let the image of these silent worlds drift through your mind. No sound, no light, just motion without effort, carried through the vastness, one orbitless moment at a time. Stars are often imagined as brilliant points of light scattered across the sky, distant and untouchable. But in the universe, stars are not brief flashes. They are long, patient processes, unfolding over spans of time that dwarf human history. A star does not simply shine. It balances. Every star begins as a quiet gathering. In cold regions of galaxies, clouds of gas and dust drift slowly, barely moving at all. Over time, gravity draws these clouds inward. The process is gentle, often taking millions of years. There is no sudden ignition, only gradual compression. As a cloud contracts, it spins slightly faster, flattening into a disk. At the center, material becomes denser and warmer. When temperatures rise high enough, hydrogen nuclei begin to fuse into helium. At that moment, a star is born, not with an explosion, but with a steady glow. This fusion releases energy that pushes outward, balancing the inward pull of gravity. A star exists in this state of equilibrium for most of its life. It is neither expanding nor collapsing. It is simply maintaining balance moment by moment. Our sun is a typical example. It has been shining for about 4.6 billion years and will continue for billions more. Every second, it converts millions of tons of hydrogen into helium, releasing energy that travels outward through layers of plasma before escaping as sunlight. This process is so stable that the sun's brightness changes only slightly over long periods. The light from a star takes time to escape. Photons created in the core may take thousands or even millions of years to reach the surface, bouncing and scattering along the way. When sunlight reaches Earth, it carries energy that began its journey long before the first humans existed. Stars come in many sizes. Small stars, known as red dwarfs, burn their fuel slowly and efficiently. They can shine for trillions of years, far longer than the current age of the universe. These stars are dim, steady, and enduring. They do not rush through their lives. Larger stars burn hotter and faster. They shine brilliantly but live shorter lives, sometimes only millions of years. Their intense fusion creates heavier elements in their cores, layering like the rings of an onion. When their fuel runs out, they can no longer maintain balance. Yet even the end of a star's life is not necessarily violent. For stars like our sun, the final stages unfold gently. As hydrogen in the core is exhausted, the star expands into a red giant, its outer layers drifting outward. Eventually, it sheds these layers, forming a glowing shell of gas called a planetary nebula. The core remains as a white dwarf, cooling slowly over billions of years. A white dwarf is incredibly dense, containing a mass similar to the Sun's within a volume similar to Earth's. It no longer produces energy through fusion. It simply radiates leftover heat, fading gradually, without drama. Massive stars follow a different path. When they exhaust their fuel, gravity overwhelms them, leading to collapse and explosion. These supernovae scatter heavy elements into space, enriching the galaxy. But even here, the process is governed by physics, not chaos. The explosion is the release of imbalance, not anger or destruction. The remnants of massive stars include neutron stars and black holes. Neutron stars are incredibly compact, spinning rapidly and emitting beams of radiation. Black holes, often misunderstood, are regions where gravity becomes so strong that not even light can escape. They are not cosmic monsters, but natural outcomes of stellar evolution. Stars do not burn evenly forever. They change slowly, subtly. Their brightness, size, and temperature evolve over time. These changes shape the environments of surrounding planets, influencing climates, atmospheres, and the potential for life. Binary star systems are common. Many stars form in pairs or groups, orbiting a shared center of mass. These systems can exchange material, altering each other's evolution. Some stars gently siphon gas from their companions, glowing brighter as a result. Others dance around each other in long, graceful orbits. Clusters of stars form together from the same cloud. They share similar ages and compositions. Over time, these clusters slowly disperse, their stars drifting apart, becoming part of the broader galaxy. The Sun itself was likely born in such a cluster, alongside many siblings that have since scattered. When you look at the night sky, you are seeing stars at different stages of their lives. Some are young and hot, others are mature and stable. Some are nearing the end of their journeys. The sky is a snapshot of stellar life cycles frozen in light. Stars also influence the structure of galaxies. Their collective gravity shapes orbits. Their radiation and winds push gas around, triggering or suppressing new star formation. Galaxies evolve as their stars age, gradually changing in color and brightness. Over extremely long timescales, star formation will slow. Gas will be used up or locked away in remnants. The universe will grow dimmer, not suddenly, but gradually, like embers cooling after a long fire. And yet, even in this distant future, stars will not vanish entirely. Long-lived red dwarfs will continue to shine softly. White dwarfs will persist as faint points of heat. Neutron stars will spin quietly. The universe does not erase its creations, transforms them. There is a quiet lesson in the lives of stars. They do not strive or resist change. They respond to balance and imbalance, adjusting naturally. Their existence is not about permanence, but about process. The light that reaches you tonight from a star began its journey long ago, traveling across space, unaffected by your concerns or schedules. It arrives steadily without expectation. In that light, there is patience. As we move on, we will explore some of the most misunderstood objects in the universe, not as sources of fear, but as calm expressions of gravity and time. We will approach them slowly, without urgency, and see how even the most extreme environments follow quiet rules. For now, let the image of stars linger, burning slowly, balancing forces, shining not to be seen, but because that is what balance creates. Black holes are often portrayed as violent or dangerous, but in reality, they are among the calmest objects in the universe. They do not roam through space seeking to consume. They remain where they form, shaping their surroundings gently through gravity, just as stars do, only more intensely. A black hole is not an absence of structure. It is a concentration of it. At its simplest, a black hole is what remains when a massive star has completed its life cycle. When such a star exhausts its fuel, gravity pulls its core inward. If the core is massive enough, no known force can stop the collapse. The material compresses into an extremely dense state, and space around it curves sharply. This curvature creates a region where escape becomes impossible. The boundary of this region is called the event horizon. Crossing it does not involve a sudden force or dramatic sensation. From the perspective of an object falling inward, nothing special happens at the horizon itself. The transition is smooth. The event horizon is not a surface you could touch. It is a boundary defined by geometry, not matter. Inside it, paths through spacetime lead inward, toward the center. Outside it, paths can still lead away. The horizon marks the point where outward paths disappear. From far away, black holes behave like any other object of the same mass. If the sun were replaced by a black hole of equal mass, the planets would continue their orbits unchanged. Gravity depends on mass, not on whether that mass is compressed into a star or a black hole. Black holes do not pull more strongly at a distance than stars do. Their influence becomes extreme only very close to them. Space around a black hole is not violent by default. It is only deeply curved. Time behaves differently near a black hole. As an object approaches the event horizon, time for that object slows relative to distant observers. From far away, it appears as though the object never quite crosses the horizon, fading and slowing indefinitely. From the object's own perspective, however, time flows normally, and the crossing occurs in finite time. This difference in perspective is not a contradiction. It reflects the flexible nature of time in strong gravitational fields. Time is not universal. It adapts to curvature. At the center of a black hole lies what physics calls a singularity, a region where density becomes extreme and current equations break down. This does not necessarily mean infinity in a physical sense. It means our models are incomplete. Nature may smooth out these extremes in ways we do not yet understand. Black holes can vary greatly in size. Stellar mass black holes form from collapsing stars and contain a few times the mass of the Sun. Supermassive black holes, found at the centers of galaxies, contain millions or billions of solar masses. These giants likely formed through gradual growth, merging with other black holes and consuming surrounding material over time. Despite their name, black holes are not completely black. When matter falls toward them, it forms a swirling disk called an accretion disk. Friction and compression heat this material, causing it to glow brightly. Some of the brightest objects in the universe are powered by black holes, not because of what falls in, but because of what happens just before. These glowing regions can emit jets of particles that extend far beyond the galaxy itself, guided by magnetic fields. Even these jets are not explosions in the chaotic sense. They are structured flows, aligned and steady over long periods. Black holes also slowly lose mass over time through a process known as Hawking radiation. This radiation is extremely faint for large black holes, making the process unimaginably slow. A stellar mass black hole would take far longer than the current age of the universe to evaporate. Supermassive black holes would persist for timescales beyond ordinary comprehension. In this way, black holes are not eternal prisons. They are long-lived structures that change gradually. They do not erase information abruptly. Modern theories suggest that information may be preserved in subtle ways, spread across the horizon or encoded in correlations we do not yet fully understand. Black holes are common. Our galaxy likely contains millions of them. They drift quietly, mostly unnoticed. Some orbit companion stars, drawing material slowly. Others exist alone, remnants of ancient stars, traveling silently through the galactic disk. At the center of the Milky Way lies a supermassive black hole known as Sagittarius A star. It has a mass of about 4 million suns. Despite this, it is currently relatively calm. Stars orbit it in predictable paths, completing loops over decades. The black hole anchors the galaxy without disturbing it. This presence is not threatening. It is stabilizing. The galaxy has grown around it, shaped by its gravity but not dominated by chaos. The center of our galaxy is not a place of destruction, but of balance. If you were far from a black hole, you would notice nothing unusual. Space would feel normal. Time would pass normally. The night sky would look unchanged. Black holes do not announce themselves unless you are very close. Even then, falling into a sufficiently large black hole could be surprisingly gentle at first. Tidal forces would not become extreme until deep inside. There would be no sudden pull. Gravity would increase gradually. Black holes remind us that extreme does not mean frantic. The universe allows for regions of intense curvature without noise or urgency. Gravity does not shout. It bends. In the long future of the universe, black holes may become some of the last remaining structures. As stars fade and galaxies drift apart, black holes will persist, slowly evaporating over unimaginable timescales. They are not endpoints, but long chapters. There is something quietly comforting in this. Even in its most extreme expressions, the universe remains lawful, patient, and calm. Nothing is rushed. Nothing is wasted. As we continue, we will shift our attention from individual objects to larger structures once again. We will drift into galaxies themselves, not as collisions or explosions, but as slow dances through time. For now, let the idea of black holes rest softly, not as threats, but as deep stillness, places where space and time fold inward, held gently by gravity. Galaxies are not static islands of stars. They are living systems, shaped by gravity, motion, and time. Though they appear fixed in the night sky, galaxies are always moving, always changing, but at a pace so slow that it feels eternal. Their transformations unfold over hundreds of millions or billions of years, far beyond the rhythm of human life. A galaxy begins as a subtle gathering. In the early universe, small fluctuations in density allowed gravity to draw matter together. Dark matter formed vast halos, and ordinary matter settled into them, cooling and condensing. Over time, stars ignited, and the first simple galaxies took shape. As these early galaxies evolved, they interacted with their surroundings. Some grew by forming new stars from internal gas. Others grew by merging with neighbors. These mergers are not sudden collisions, but long, graceful encounters. Two galaxies can pass through each other over hundreds of millions of years, their stars mostly unaffected, like distant dancers weaving through shared space. When galaxies merge, their shapes distort slowly. Spiral arms stretch and bend. Tails of stars extend outward like streams of light. Eventually, the systems settle into a new equilibrium, often forming a larger, smoother galaxy. These events do not destroy galaxies. They transform them. Our own Milky Way has grown through such mergers. Its stars carry the record of these ancient encounters in their motions and compositions. Streams of stars still arc through the galaxy, remnants of smaller systems absorbed long ago. Galaxies come in many forms. Spiral galaxies, like the Milky Way, have rotating disks with sweeping arms where star formation continues. Elliptical galaxies are rounder and smoother, often containing older stars and little gas. Irregular galaxies lack defined shapes, shaped by interactions and internal turbulence. These forms are not permanent. A spiral galaxy can become elliptical through mergers. An irregular galaxy can settle into a more orderly structure over time. Shape reflects history, not destiny. At the centers of most large galaxies lie supermassive black holes. These objects grow alongside their galaxies, their masses correlated with the properties of surrounding stars. This relationship suggests a deep connection, a quiet feedback between gravity, energy, and structure. Galaxies are not isolated. They gather in groups and clusters, bound together by gravity. The Milky Way is part of a small group that includes the Andromeda Galaxy and many smaller companions. Over billions of years, these galaxies will slowly approach one another. In about 4 billion years, the Milky Way and Andromeda are expected to begin merging. This will not be a catastrophic collision. The vast distances between stars mean that direct impacts are unlikely. Instead, the galaxies will interweave, their shapes stretching and blending, forming a new system sometimes called Milkomeda. During this process, the night sky as seen from Earth will change gradually. Andromeda will grow larger, its spiral arms visible to the naked eye. Over time, stars will shift positions, creating new constellations. The process will take hundreds of millions of years, giving plenty of time for change to unfold gently. Galaxies also rotate. Stars orbit their centers in long, steady paths. In spiral galaxies, this rotation creates patterns like arms, where density waves move through the disk, triggering star formation. The arms themselves are not fixed collections of stars, but regions where stars and gas bunch together briefly before moving on. Between galaxies lies intergalactic space, filled with thin gas, dark matter, and faint radiation. Galaxies exchange material with this environment, drawing in gas and occasionally losing it. The boundary between a galaxy and the space around it is not sharp. It fades gradually. Clusters of galaxies are some of the largest bound structures in the universe. They contain hundreds or thousands of galaxies, along with vast amounts of hot gas that glows in X-rays. This gas holds more mass than all the stars combined, yet remains diffuse and calm. Gravity within clusters bends light from background objects, a phenomenon known as gravitational lensing. This effect allows astronomers to map dark matter distributions. Light curves gently around mass, tracing invisible structures. Even light responds to the slow dance of gravity. On even larger scales, clusters connect into filaments, forming the cosmic web. These filaments stretch across hundreds of millions of light years, linking galaxies like beads on threads. Between them lie voids, immense regions with few galaxies, emphasizing the universe's delicate structure. Despite this vast organization, galaxies are not aware of their place in the web. They follow local rules, responding to nearby gravity. Order emerges without intention, guided by simple principles applied over immense time. Galaxies age. Over time, they consume or lose the gas needed to form new stars. Star formation slows, and the galaxy becomes redder as older stars dominate. This transition does not signal an ending, only a change in activity. In the far future, galaxies will grow quieter. Fewer new stars will appear. Existing stars will age and fade. The universe will become dimmer, but not empty. Structures will persist, slowly evolving. There is a peaceful symmetry in galaxies. Billions of stars orbiting quietly, bound by gravity, each following its own path, yet contributing to a collective form. Chaos at small scales gives rise to harmony at large ones. When you look at a galaxy through a telescope, you are seeing not a moment, but a long story compressed into light. Each point is a star, each glow a region where processes unfold slowly and steadily. As we continue, we will turn toward the future, exploring what lies ahead for the universe as a whole. Not endings in a dramatic sense, but long, gradual transitions that stretch far beyond imagination. For now, let the image of galaxies drifting through space rest gently in your mind. No hurry, no destination, just motion balanced by gravity, unfolding across time. When we imagine the future of the universe, it is easy to think in terms of endings. But on cosmic timescales, change rarely arrives as a sudden conclusion. Instead, it unfolds gradually, like twilight deepening into night. The universe does not rush toward silence. It drifts there slowly, almost imperceptibly. One of the most widely discussed possibilities for the universe's future is known as the heat death. Despite its name, this is not an event, but a condition. It describes a universe that has reached a state of maximum entropy, where energy differences have evened out and no significant work can be done. In such a universe, stars no longer form. Existing stars eventually exhaust their fuel. Galaxies grow dark. Yet this process unfolds over timescales so vast that they resist ordinary comprehension. Trillions upon trillions of years would pass before the universe approaches anything resembling this state. Before stars fade, long-lived red dwarfs will dominate the cosmos. These small, steady stars burn their fuel slowly, shining faintly for trillions of years. Long after galaxies like ours have ceased forming new stars, red dwarfs will continue to glow softly, providing quiet points of light in an otherwise darkening universe. As time stretches onward, stellar remnants become more common. White dwarfs cool gradually, fading into black dwarfs over unimaginable spans of time. Neutron stars spin more slowly, their beams weakening. Black holes remain, outlasting nearly everything else. Black holes themselves will eventually change. Through Hawking radiation, they slowly lose mass, releasing energy in tiny amounts. For supermassive black holes, this process would take far longer than the current age of the universe multiplied many times. Even so, the process is gentle. Evaporation happens without drama. Long before black holes fade, galaxies may drift beyond each other's reach. As the universe's expansion accelerates, distant galaxies will move away so quickly that light emitted from them can no longer reach us. Over time, the observable universe will shrink, leaving only the local group of galaxies visible. From within such a future, observers would see a darker sky, not because stars have vanished, but because the universe has grown too large. The light is still out there, traveling through space that expands faster than it can cross. This future is not empty of structure. Gravitationally bound systems remain intact. Stars continue orbiting within galaxies. Planets continue circling their suns. Local order persists even as large-scale connections fade. Some theories suggest the universe may not continue expanding forever in the same way. In certain models, dark energy could weaken or change, allowing expansion to slow or reverse. The universe might contract, leading to a new phase of compression. In these speculative models, contraction would not necessarily mean a violent collapse. It could be gradual, symmetrical to expansion, perhaps leading to a bounce that gives rise to a new expansion. Each cycle could erase large-scale structures while preserving deeper patterns. Other ideas propose that our universe is one of many, each with its own physical constants and histories. In such a multiverse, universes could emerge, evolve, and fade without affecting one another, like bubbles forming in a vast, timeless sea. These ideas remain untested. They are not predictions, but possibilities. The universe allows room for uncertainty. It does not demand that we know its final chapter. What is consistent across these scenarios is the absence of urgency. Nothing in the universe suggests a countdown. Time stretches generously. Processes unfold at scales that render haste irrelevant. Even as stars fade and galaxies drift apart, the universe remains governed by gentle laws. Energy redistributes, matter transforms, structure simplifies. There is no collapse into chaos, only a gradual smoothing. In the far future, particles themselves may decay. Protons, once thought to be stable forever, might slowly break down into lighter particles. If so, matter would gradually dissolve into radiation and fundamental components, further smoothing the universe's energy landscape. Yet even this would not be sudden. Each decay would occur quietly, one particle at a time, across enormous spans of time. Nothing would notice the change at first. Throughout all of this, space-time remains. The framework persists even as contents change. Space continues to expand or evolve. Time continues to unfold. The future universe may be simple, but not empty. It may be quiet, but not gone. It may be dark, but not erased. There is something peaceful in this vision. The universe does not end. It settles. It releases complexity slowly, without resistance. From our perspective now, this future is so distant that it does not demand concern. The stars will shine for far longer than humanity has existed so far. Planets will continue orbiting. Galaxies will remain vibrant. The universe is not fragile. It does not teeter on the edge of collapse. It is stable, resilient, and patient. As we move toward the final parts of this journey, we will turn from cosmic futures back toward meaning and perspective. Not in a philosophical sense, but in the quiet recognition of how deeply we are embedded in these vast processes. For now, let the idea of the far future rest gently. There is no ending approaching, only a slow, graceful unfolding that stretches far beyond thought. As we think about the universe across immense spans of time, it becomes natural to wonder whether it truly has a beginning or an end. Human stories tend to follow a straight line. They begin, unfold, and conclude. But the universe may not follow this pattern at all. It may move in cycles, rhythms, and recurring phases that stretch far beyond anything we can easily imagine. Some cosmological theories suggest that the universe may be eternal in some form. Not eternal in the sense of remaining unchanged, but eternal in its ongoing transformation. In these ideas, what we call the beginning may simply be a transition, one phase giving way to another. One such idea is the cyclic universe. In these models, the universe expands, slows, and eventually contracts. After reaching a dense state, it rebounds, beginning a new expansion. Each cycle could last trillions of years. Each one could reset large-scale structures while preserving deeper physical laws. If this is true, then the universe we see today would not be the first. There may have been others before it, each with its own galaxies, stars, and histories. Their traces would be faint, subtle, woven into the fabric of space-time itself. Another idea suggests that our universe exists within a larger multiverse. In this view, universes emerge the way bubbles form in boiling water. Each bubble expands, develops its own physical rules, and evolves independently. Some may collapse quickly, others may persist for vast lengths of time. Our universe may simply be one that happened to support long-lasting stars, stable atoms, and complex structures. Not special by design, but by circumstance. These ideas do not diminish the universe we inhabit. Instead, they place it within a broader context. A reminder that existence may be more spacious than our observations suggest. What makes these possibilities calming rather than unsettling is their scale. Nothing happens abruptly. Universes do not flicker on and off. Everything unfolds slowly, following consistent rules. Even the birth of a universe, if such events occur repeatedly, would not resemble an explosion in space. It would be an expansion of space itself, a gentle unfolding from an extremely compact state. Time, in this sense, may not be a straight line. It may be more like a wave or a series of overlapping currents. Each moment flows into the next without sharp boundaries. From within the universe, we experience time locally. We measure it with clocks, calendars, and biological rhythms. But on cosmic scales, time may behave differently, stretching, looping, or branching in ways that feel abstract from our perspective. Some theories suggest that all moments exist equally, that past, present, and future are part of a single space-time structure. In this view, time does not move. We move through it. If so, then every calm night sky, every distant galaxy, every quiet moment of awareness already exists somewhere within the universe's structure. Nothing is truly lost. Nothing fully disappears. This does not mean the universe is static. Change still happens. Stars still form and fade. Galaxies still drift. But all of these changes are woven into a larger, timeless pattern. The idea of cycles also appears in smaller ways. Stars are born from clouds of gas enriched by previous generations of stars. Planets form from recycled material. Atoms in your body were once part of ancient stars that lived and died long before the sun existed. In this sense, the universe already practices renewal. Matter moves through phases, returning again and again in new forms. Even energy, which cannot be destroyed, only changes shape. Light becomes heat. Heat becomes motion. Motion becomes structure. Structure dissolves back into simpler forms. Nothing is wasted. Everything participates. When viewed this way, the universe feels less like a machine racing toward shutdown and more like a slow, breathing system, expanding, transforming, redistributing. This perspective allows space for calm. There is no final moment rushing toward us. No cosmic deadline. The universe is patient beyond comprehension. The night sky we see today is a snapshot, a single frame in an unimaginably long sequence. It does not need to tell the entire story, and we do not need to understand every possibility for the universe to be meaningful. Mystery does not imply danger. Uncertainty does not imply instability. The universe has existed for billions of years without awareness. It will continue for billions more regardless of observation. Its rhythms do not depend on being witnessed. Yet here we are, able to notice, to wonder, to rest beneath its quiet vastness. There is something deeply soothing in knowing that the universe does not require urgency from us. It unfolds whether we hurry or pause, whether we worry or rest. Cycles continue. Possibilities remain open. The story is not confined to a single arc. As we approach the final part of this journey, we will gently bring our focus closer again. Not away from the universe, but into our place within it. Not as something separate, but as something naturally included. For now, let the idea of endless rhythm settle softly. No beginning pressing behind you. No ending waiting ahead. Just a vast, steady unfolding that continues calmly, without strain. As this journey through the universe gently draws toward its resting point, there is no need to rush toward an ending. The universe itself never truly stops. It simply changes pace, moving from brightness to dimness, from activity to rest, from structure back into quiet potential. For a moment, imagine the universe not as something far away, but as something that includes you completely. Every atom in your body was shaped by ancient processes that began long before Earth existed. The carbon in your cells, the oxygen in your breath, the calcium in your bones, all were formed inside stars that lived and faded billions of years ago. You are not separate from the universe. You are one of its expressions. The same physical laws that guide galaxies also guide the smallest movements within your body. The same gravity that shapes planets quietly holds you to the Earth. The same energy that lights distant stars once flowed through the early universe and continues to move through everything now. Nothing about your existence is out of place. When you look at the night sky, it may seem distant and silent. But in truth, the universe is constantly interacting with you. Light from distant stars passes through your eyes. Cosmic particles pass harmlessly through your body every moment. The universe is not watching from afar. It is already here. This sense of belonging can be calming. It softens the feeling of being small or alone. Smallness, in this context, does not mean insignificance. It means being part of something vast and well-ordered, something that does not demand effort to belong. There is no requirement to understand the universe in order to be part of it. Stars do not need to comprehend gravity to shine. Galaxies do not need awareness to form beautiful spirals. And you do not need answers to rest within the natural flow of existence. The universe does not rush. Even the fastest processes unfold over timescales that dwarf human concerns. The expansion of space itself is slow and steady. Stars burn for billions of years. Galaxies drift at a pace that feels almost still. This slowness is not emptiness. It is stability. And that same stability is reflected in quieter moments within you. When the breath slows, when the muscles soften, when the mind releases its grip on planning and remembering. In these moments, you align with the universe's deeper rhythm. Sleep itself is a kind of return, a temporary release of awareness back into a more fundamental state. The universe does not resist this. It welcomes it. As you rest, your body continues its quiet work. Cells repair, memories settle, systems rebalance. None of this requires effort or control. It happens automatically, guided by processes refined over billions of years of evolution. Even your thoughts, as they slow and drift, are part of this natural order. They are not interruptions. They are gentle currents that gradually lose their force. If a thought appears, there is no need to follow it. Like a distant star, It can remain where it is without drawing you closer. You can simply notice it, then allow your attention to soften again. The universe is filled with vast, silent spaces between objects. These spaces are not empty. They are fields, potentials, quiet connections. In a similar way, the spaces between your thoughts are not gaps to be filled. They are restful places. It is often in these quiet spaces that calm arrives. There is no pressure to reach a specific state. Rest is not something to achieve. It is something to allow. The universe does not judge whether a galaxy forms quickly or slowly. It does not demand perfection from stars. It allows variation, irregularity, and change. You are afforded the same freedom. You can rest imperfectly. You can drift in and out of awareness. You can remain awake a little longer without concern. The universe has patience far beyond any schedule. Somewhere far beyond our view, stars are forming in dense clouds of gas. Elsewhere, old stars are cooling, their light slowly fading. Black holes quietly gather matter. Galaxies continue their slow dances. None of this needs your attention to continue. You are free to let go. As this narration gently settles, it does not mark an ending, only a pause, a soft return to stillness. The universe remains, steady and vast, holding everything without effort. You may drift into sleep now, carried by the same calm processes that guide stars and time itself. And if this journey begins again, it will do so gently without disruption. Like a cycle, like a breath. For now, rest. The universe will continue quietly as you do.